Hi, I'm Shashwat Gupta. I'm the engineering manager at Azure AD.
Hi, I'm Vadit Raman, Engineering Manager at Azure AD. Today we're going to talk about a use case where we used Azure Cosmos DB as a log service to provide uniqueness across a distributed system. Before going into the problem statement, I'll give you a background about Azure Active Directory, also known as Azure AD. Azure AD is a cloud-based identity and access management service. It lets you securely manage access to your Azure services and resources for your users. Azure AD, architecturally speaking, is a geographically distributed service that has high availability and high performance. The Azure AD data tier is divided into scale units. Each scale unit is called a partition. To connect with the Azure AD data tier, we have front-end services that provide read and write capabilities. The picture on the left shows you the components of a single directory partition. We have the primary replica that takes the writes. To ensure geo-redundancy of writes, any write to the primary replica is immediately replicated to a secondary replica in a different data center. We have secondary replicas to serve reads. The secondary replicas are located in geographically different data centers to provide high availability. The replication of data to these data centers is done asynchronously. For scalability for reads, we add more secondary replicas, and to scale for writes, we add more partitions. Now, a tenant in Azure AD is the instance for an organizational unit and all the objects that come underneath it. In Azure AD, a tenant spans a single partition. Now, let's talk about Azure AD B2C. Azure AD B2C is our special offering for business to consumer identity as a service. It uses the same technology as Azure AD, but for a different purpose. Azure AD B2C allows its customers to sign in using their social media accounts, enterprise logins, or other logins to get access to APIs and applications. It is able to support millions of users and billions of authentication requests per day. Now, to support the scale of Azure AD B2C, a tenant in Azure AD B2C spans across multiple partitions. Now that I've given you a background into Azure AD and Azure AD B2C, let's go into the problem statement. In the Azure AD schema, we have objects that have unique properties, and that means these objects need to have these properties unique across a tenant. This is how we do uniqueness checks in Azure AD. A user would send a request to a graph frontend. The graph frontend would then send this request to the primary replica of a partition. The primary replica of a partition is capable of doing uniqueness checks for the data in that partition. So after doing the write checks, the primary replica would then return a response to the graph frontend, which would then return the response to the user. And this ensures that uniqueness is maintained for that tenant. Now let's see how the same case would work for Azure AD B2C. As mentioned earlier, Azure AD B2C, the tenant spans multiple partitions. So let's say a user sends concurrent requests to the graph frontend. Now the graph frontend could send both these requests to two separate partitions. Now what would happen on both these partitions is the primary replica would do a uniqueness check for those partitions and send a response back to the graph frontend. But this response would be incorrect because it does not guarantee uniqueness across the tenant. And so the final response sent back to the user is incorrect because now the user data is violated. To solve this problem, we introduced an external locking service. Now let's go into the requirements for the external locking service. We wanted a service that is tolerant to single Azure region outages. Our B2C customers span across geos, and so we do not want a single region going down to cause a complete B2C outage. Given that we are using this lock for data consistency, we wanted a service that is highly durable and is able to hold a lock for a specified amount of time. We also wanted a service that could scale easily, so that as our B2C offering grew, we did not have to redesign our system for scale. We also wanted a highly performant system because we were using this in the right code path. And for that, we wanted a system that could offer us latencies less than 100 milliseconds. Now, in the Azure AD schema, for an object, we can have multiple unique properties. This means that when a write happens, all the properties need to be unique or the write needs to be rejected. That means when the log service is taking a lock, it needs to take a lock for all the properties, otherwise reject the locking. For this, we need transactional support, and that's why this is a requirement. Cost of ownership. Now, for managed services, the longer you host a service on a managed service, the cost keeps going up. And so we would like a service that had a low cost of ownership. Now, we wanted a service that had a TTL-based cleanup because we wanted to implement an auto-release for locking mechanism. Given all these requirements, we looked into various services, but we did a deep dive mainly on two, Redis and Cosmos DB. Now for Redis, it had a very low cost of ownership, but the durability and availability was not the best. Cosmos DB gave us very good durability and availability and overall supported our needs the best. Now we'll hand over to Shashwat to walk you through our implementation of the Cosmos DB log service.
Before I describe our end-to-end flow, let's review what exactly we are storing in our Cosmos DB. We store objects' unique property values as a keys and the object ID and object class combination as the value. Basic idea is that Cosmos DB provide uniqueness guarantees on its keys and index. So if property values can be stored in Cosmos DB, the lock is guaranteed. Let's review this with the example. Here we have a user Adelv at Contoso on Microsoft.com who is getting created by the admin. Here the mail nickname and the user principal name are the unique values. In this case, we will create these two entry in the Cosmos DB. Furthermore, we want to ensure uniqueness only across tenants. So we use tenant ID as the partition key here. The TTL of the values are 15 minutes. Now take our review our end-to-end flow. As Vandit was explaining, Azure AD is a multi-partition system. Here we have for each partition one single primary replica and multiple secondary replicas. Secondary replicas primary takes reads, while primary replicas takes the write. We have a replication mechanism that is going from primary replica to secondary replicas, and with the maximum 15-minute replication delay. If there is a replication delay more than 15 minutes, we will throw service unavailable exception. Here are the other component of the system: Cosmos DB, Graph Frontend, and the user. Cosmos DB have all the fresh data for last 15 minutes, and the secondary backend has the complete data for more than 15 minutes. So when the user posts the request to Graph Frontend, the Graph Frontend makes a concurrent calls to all the secondary replicas where the tenant could be present, as well as to the Cosmos DB. Once we hear back the response, we make a request to the primary replica to actually write the object. Let's take an example at time 0. Here the user principal name Adelv at Contoso on Microsoft.com is getting posted to Graph Frontend. Graph Frontend receives this request and makes a concurrent calls to all the secondary replica for uniqueness check. Because the user is not present currently in these secondary replicas, these replicas return back the no uniqueness check violation. In that case, we go ahead and Cosmos DB reserve the keys. Subsequently, we call frontend makes a request to the primary replicas to write the actual user object. Now let's take an example. What happens if a concurrently another user makes a request for the same user principal name? Again, the request is received by the Graph Frontend, and Graph Frontend posts the request to all the secondary replicas. Secondary replicas again would return no uniqueness violation because it's possible that the data has not been replicated. But the Cosmos DB would return the error in this particular case for reserving the keys, because Cosmos DB being strongly consistent, there is a guarantee that the key won't be able to reserve. And in that case, Graph Frontend would return back the uniqueness violation to the user. Let's take an example. What happens when the same request came at the 16 minute? I'm using 16 minute because 15 minute is the TTL for this Cosmos DB. Request is received by the Graph Frontend. Graph Frontend again sends a request concurrently to secondary replica as well Cosmos DB request to reserve this key. In this particular case, secondary replicas throws back a uniqueness violation while the Cosmos DB is able to reserve key. At this point, Graph Frontend knows that there is a uniqueness violation, so it return back the uniqueness violation to the user. But before doing that, it delete the reserved key that was done for Cosmos DB. Now let's see what happens in the delete and modify scenario. A delete request for this user comes to graph frontend. Graph frontend makes a request to primary replica to delete the keys, but after that it makes a reserve key request with the sentinel value to Cosmos DB, and then it return back the result to the user. Now this with using the sentinel value allow us to use this value again for the subsequent caller. So in this case another user is making a post request with the same user principal. Ideally this user principal should be now available for to be used by the user with the new user. Here we have a graph frontend sending requests to the secondary replicas as well as to Cosmos DB. In this particular case, one of the replica may possibly return uniqueness violation because the data information about the previous delete has not been propagated to secondary replica. But Cosmos DB is able to write conditionally update that value because we have previously reserved the value with the sentinel value. In this way, we can handle all the delete scenario as well as modify scenario. We use stored procedure in the Cosmos DB. It allows us to batch update to ensure transaction. In my examples previously, we use single unique value, but in practice we have multiple unique values across objects, and so we want these all unique values to be either preserved or not preserved. We want to send a write error message to caller. For example, we just don't want to tell whether there is a conflicted object present, but we want to tell what exactly object it's conflicting with. And we want to do conditional update, as we saw in case of delete scenario, where we want to update the sentinel value to the actual object ID and object class value. So let's review how is it working in the production. We have set up our Cosmos DB with the auto scale. We have multi-read region setup, and it allows us to be resilient to Azure region outage. We have multiple regions, and each region has multiple accounts. And with our setup, we are serving up to 75K provision requests. That means create or delete or update requests across tenants. That is all for our presentation. Please reach out to our LinkedIn or Twitter handle mentioned in this slide for any kind of questions or feedback, or if you want to share any your own implementation with us. Thank you.